Okay, so today we're going to talk about another variance reduction method. Okay, so this method is called importance sampling. Okay, so this is how it works. All right. Now suppose we have as usual, right? So we have some function that we want to evaluate. Okay, so let's say okay, we want to evaluate this integral, right? This this omega is actually the samples. So your sample space, okay, for your random variable x, right? So basically, you're integrating over. Well, maybe not the samples. Well, yeah, you can call it the sample space, okay, or just maybe just a space, right? Because it need not be a integrating to one. Okay, anyway, so you get the idea, right? Now, so of course, for example, this could be something like some function like this, okay? For example, right? Now, we could actually rewrite this as follows, right? In fact, this is what we generally do. Hx of fx dx, right? Where your f of x here is actually a probability density function, right? And its support is so it has the same support, right? That means integral of fx dx over, and now it's a sample space, right? So this is 1, okay? So we write it like this, and of course that allows us to write it as the expectation of h of x, right? We denote f here, where your x has probability density function f of x, okay? Right, okay? So this is the standard approach. So of course, then your Monte Carlo estimator for theta would be a summation of h of xi over sum n over n, right? Where your x1 until xn are ID from f of x, okay? So that's the usual situation, right? Now, we could actually push this one more step, okay? So we could push it one more step and let it be the following, okay? So we could actually write theta equals to hx fx divided by gx, then you cancel off the gx and dx, right? Okay. So this would still be the same, except that now, of course, I will treat my gx. This is another PDF. Okay, it has to be a PDF. So this would be written as the expectation of hx fx over g of x, right? Now this whole thing here, you'll treat it as some function of x, right? And they are all drawn from a density of g of x, right? So that's why you can bundle them together like this. And basically this is with respect to g, right, as the density, okay? So where my x is drawn from the x as PDF g of x. Okay. Right. Okay. So it's just one additional step here where we introduce another function, another density function, right? And we take the ratio of hx fx over gx, right? Okay. So far, so good, everyone.
Yes.
Okay. So you would actually take the Monte Carlo estimator, maybe let's say star. So this would be summation h xi fxi over g of xi, right? And okay, where your x1 until xn are IID from g of x. Okay. All right. So instead of drawing from f, now you draw from g. All right. Okay. So I'll just erase some of these things here. All right. So okay. So the next step is for us to evaluate the variance. Okay. We do some analysis about the variance of this Monte Carlo estimators, right? So we are interested to find out the variance, okay, of the variance of this whole thing, right? Okay, so basically this is the variance of theta hat star is equal to 1 over m, the variance of h x f x over gx. Okay. Actually, there's a 1 here, but it doesn't matter, right? So the RIID, okay? So for simplicity, I'll just write the big X, okay, without the subscript, okay? So we need to evaluate this variance, right? This is just a constant term. This is actually n, right? So we want to find this variance, and how do we find this? Okay, it looks kind of like complicated, but actually we may not actually need to evaluate it totally, but just to find some kind of bound for it. Okay, so so by definition, right, this part here is equal to, so this whole part here, right, is equal to the expectation of the square, right? Subtract the square of the expectation, okay? Right, okay? Now, this expectation here, this part is your theta, right? Okay? Right, okay? Comes from here, right? By definition itself. So the expectation of this over G, okay, is actually theta itself, okay? So we just need to evaluate this expectation, right? Now this expectation is h x f x gx squared, right? And remember it's over G, right? So it's multiplied by g of x dx, okay? So if you simplify this, right? So it becomes the following. You can write it like this. All right, okay. So just cancel off the gx, so you have only a single gx in the denominator. But the numerator, I just split it up into the square. I just write it like this, right? Now the purpose is to do the following. Okay, so now this is one thing here, right? Okay, now we could actually, so this is some kind of function, right? If you do some sketch, it could be some, doesn't matter, it's just some function, right? Okay, this whole thing here, okay? hx, fx, gx, okay? This is definitely bounded by, if the function goes like this, right? It's definitely bounded by the global maximum, okay, of this function. So this line here, right, is the max of hx, fx over gx, right? Right? It doesn't matter how complicated this function is. There will be a max, right? Okay. So you could take that max. So definitely, so this guy here is definitely bounded by the max. Okay. That means this integral, right? You're finding the area under this curve, right? It's definitely bounded by the area under the entire rectangle here, bounded by the max. Okay. So that's actually, it's actually not a very hard idea. It's a simple one. So you have the max of this, okay? Of course, it's over x times hx, fx, dx, okay? And this, of course, gives you, you could take this out because the max is a constant, right? So let's say I take this out, okay? And I write it as m. All right, I write it as m. So this would be integral of hx, fx. So this whole thing here is m of theta, right? Because this thing here is actually theta. Okay, if you look at the definition of theta at the beginning. Okay, so basically we have a result for the bound, right? So basically the result is this variance here is bounded by m theta minus theta squared, right? This thing, okay? So it's basically equal to theta times m minus theta, okay? All right, so there is a bound there, right? Okay. So this bound will help us find the variance. Okay, for example, once you have constructed a Monte Carlo estimator, you want to find its variance, but this may be very difficult to evaluate. Okay, so as usual, if you have studied your probability theory, right? Sometimes if direct evaluation is hard, then we use the idea of bounds, right? We find that because bounds are usually easier to find than exact evaluations sometimes, okay? So you just find the bound, right? And then you work with the bound, all right? Okay, so we know that it has, so it's bounded by m times theta minus theta square, right? So this is an important constant here. Okay, so let me just write it down at the corner. So my m is the max of hx fx over gx, okay, over my x. All right. Okay, so this variance here will not exceed this amount. Okay. Now let's take a look at an example. So we need an example to fix ideas. All right. So let me clear the slate here. Okay, an example. Okay. Right. Suppose we want to find out this integral. Okay. So this is a function that so this alpha is some positive constant, and this a is also some positive constant, right? So basically this
Doctor.
Yeah.
Someone can enter.
Who?
Zulaika.
Sulaika. I don't see anyone. Let me see. Okay, check. I don't see anyone in the waiting room. Can she try again?
Right.
Okay, ask her to click again. All right. Okay. So generally, is some kind of a curve, right? All right. You look at this part here. So this a here. So you're integrating from starting from a, right? So it's some curve that maybe looks like this. Okay. Right. You are integrating here. Right. So over here, there's nothing, right? Actually, well, actually, this curve here, you could actually draw it completely. Let me see. Okay, doesn't matter. Okay, so by right is the whole thing, right? But since you only want the integral from a to onwards, right? You basically want this, right? This is actually the same equivalent as finding an integral, whereby the curve, instead of is this whole thing, it is just this part, right? Where this part is 0, because you're not integrating it, right? So you could treat it as that. You might as well treat it as 0, right? Okay. So this is an important idea later. Okay. Okay. Sulaika still has problem. I can't see her.
She said she already requested again.
We already requested. Let me see. Okay. Let me try something here. So I just sent a link to Zuleika. So in Flock. So maybe she can click on that and let's try again. Okay. While we wait, so let me just continue. Right. Okay. So you're gonna find this integral. Okay. Now this one. Okay. So we can actually write it as the following. So we're going to use importance sampling to do this. Okay. Right. Now, if you are going, so this whole thing here is my v of x, right? So I'm going to split it into hx and fx, okay? Now, suppose if you use, if you consider fx, okay, as the exponential function, right? So you'll have to integrate from 0 onwards, okay? Right, because your exponential function is actually, the support is from 0 to infinity, okay? So then this part here, you will have to use indicator function to do it, okay? So the way to do it is, so this part here is your fx. So you want to write your hx, right? So this will be x power of alpha minus 1 multiplied by indicator function x greater than a. Okay, so this part here will be your hx, right? So pause for a while and think about it, okay? So this x power of alpha minus 1 basically is it's just some curve, right? Maybe, right? Okay. So this is a. So this is a, right? So basically, instead, so this is saying that when your x is 0, right? So this whole thing is 0, okay? Right. This indicator function, right? When the condition is x less than or equals to a, it will be 0, right? So this integral will be basically like this part here, okay? It's empty, right? So that's why this curve here is basically a curve that's like this. Empty over here, 0. And then after that, it is 1. Then multiply by that, so you get this, right? So it's like a disconnected function, okay? Right. So, but that is still a function, right? It's just not a smooth. It's just not a smooth function, okay? Right. I still can't see Zuleika here, so I don't know. Maybe she can exit Zoom and then come back again or something like that. Maybe, I'm not sure. I can't see anyone at the waiting room. Okay. Anyway, it's recorded, so she can watch it later. Right. Okay. So now, if you do this, right, then your Monte Carlo estimator will be the following, right? The expectation of h of x, right? So that will be x power of alpha minus 1 I x greater than a, okay? sorry, that's not yet. It's not, all right? So it's just the expectation, right? So your Monte Carlo estimator is here. So summation xi alpha minus 1. Okay, oops. All right, so this divide by n, right? Okay. So where your xi exponential 1, okay? Right, you draw IID from exponential, right? Now the problem with this, so this is okay, right? As an estimator, it is fine. But there is a problem with this approach, okay? So as you can see, the variance of this method will be extremely large, right? The reason is as follows. Now, so you basically you draw a random variable, variate from the exponential, right? If it is below a, like your a is some value, let's say a equals to 5 or whatever, okay? If it's below 5, then you will score a 0, okay? If it's above 5, then maybe then you will score some value, like let's say your a is 5, right? So maybe you got this, so then it will score, right? And then maybe 7.2, maybe 9.8, then 0, 0, and so on, right? So then this one, of course, you then take raise it to power of alpha minus 1 and so on, okay? The problem with this approach is that you're going to get a lot of zeros, okay? Because these are all values where this checking, right? It was not satisfied, okay? This condition was not satisfied. So you will get a lot of zeros, especially when your a is large. When your a is large, your exponential, remember your exponential density, right? Your exponential density is going down rapidly like this. So if you set your a to be very large, right? Okay, let's say your a is very large, right? Most of the time, the values that you generated, right, will be below a. So they will be scored as 0, okay? So when you simulated these values, right, what happens is you're going to get a lot of zeros here. All these terms here, you're going to get a lot of zeros, and then a lot. And then over here, you have you will have some values, right? Maybe so something like 5.4, 7.5, maybe 9 point something, and so on, until some very large values, 120, and so on, okay? Right? Now, if you do the variance, right? If you consider the variance of all these values, okay, of course, then you average them, you will get the Monte Carlo estimator. On average, you will get it quite right, okay? Its expectation will be close to the theta. But the problem is the variance here. You will see that a majority of your simulated values are 0. And then you have a bunch of values that are ranging from something close to your A, and then something very large from A. Of course, the variance is going to get very, very large. All right? It's very unstable. Okay? So basically, it's like you have a whole bunch of values stacked at 0. Okay? And then suddenly you have got values running here, 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 here on. This is A, right? So you calculate the variance here. The spread is very large, right? Okay. So for this purpose, right, a direct Monte Carlo estimation is actually not very good, right? In the sense that your variance is actually inflated. Okay. So to overcome this problem, right, then importance sampling comes in. Okay. You will see later that this importance sampling can actually reduce the variance to something that is very, very small, right? So, so we were going to talk about that, okay, in a while. So, so the meeting time, I'm only given 40 minutes for this Zoom session. The previous one, they offered me some extras, so I just took that. But the standard Zoom limit is 40 minutes and I don't have a subscription, okay? So there's still less than a minute. So I'm going to stop here for a while. We'll take a 5-minute break and then I'll send invites to everyone again, okay? Then you join, yeah? All right? Okay, everyone?
Okay.
Okay, then, yeah, then maybe Zulaika can try again to come in. Right, okay. So coming back here. Okay, coming back to this part here, right? So we just now I already mentioned the problems with a direct Monte Carlo estimator, the kind of estimator that you will construct if you had only studied the first part, right? Maybe first 2 weeks of your lecture. Okay, so in fact, so you have to change this thing here. So you want the integral to be starting from a, right? But then since if you're going to use your exponential function as the density, right, you have to change it to 0. Okay. So that means over here, your function here, you have to modify it slightly, which is you have to multiply it by an indicator function, right? So when the condition x greater than a is true, so this will be take the form of x power of alpha minus 1. Otherwise, it'll be 0. Okay. So because of that, then this becomes your hx and that's your fx. So you write your expectation as such. Okay. So this is your function, right? So this thing now is your h of x. Okay. So then your Monte Carlo estimator is basically just this thing here where your x is actually exponential 1, okay? So your x's here are drawn from the exponential function, okay? But as I mentioned just now, you have a problem with this method suffering from large variance because it will, especially when your a is large, right? So for example, if your a is maybe like 10 or something, what happens is that if you use an exponential 1, right, most of your values will be very close to small values, or because its mean is 1. So you will have most of your values being 0, okay, with a very small minority being large values, right? The exponential can actually go like very far, right? So if you generate enough, so sometimes you get some very large values, okay? But most of the time, they're all very small values. So the mean is 1 here, okay? So most of you are going to get a lot of zeros, and then, so you're going to get a lot of zeros here, and then some extreme values like this. With this kind of values, right, of course, your variance is going to be large because they're all spread out, right? So this is not good, okay? For Monte Carlo estimation, we try to make the variance as small as possible, okay? And we had several methods that we learned already using antithetic variables, using control variables. So now for this part, we learn how to use importance sampling, okay? To overcome this variance problem, all right? Okay. So I'm going to clear the board a little bit. Okay. So as you know, just now we have if you use importance sampling, right? So the your Monte Carlo estimator, you will have to introduce some GX, right? A new density, okay? So this new density has to, ideally, right, it should be similar in shape, right, to your HX, FX, okay? As far as possible, okay? So in this case, what would be a suitable example? So we will look at the, instead of actually working with the exponential, right? So we're gonna work with something called the shifted exponential. Shifted exponential is it's just a very simple form. So if, for example, if, so here I'm going to write gx equals to lambda e of minus lambda x minus a, okay, where my x is greater than or equals to a, right? So this is basically the shifted exponential. If you graph this, right, it basically is starting from a, right? And then it just comes down, okay? Right, so this is my gx, right? So basically over here, there's nothing. It's flat, okay? So in fact, you could also write your gx to be something like, if you use indicator notation, I of x greater than a. Maybe I just put larger than a, easier. Okay? So this is a shifted exponential, right? Basically, you could see that it is basically just, you're just moving it from its usual place starting from 0, and then moving it a certain number of, right? In the usual case, you just have lambda e of minus lambda x, right? So you basically just shift it by an amount a, right? So basically you can do this by, so if x is exponential lambda, right, with parameter lambda, then x plus a is your shifted exponential, right? Right, to a, okay? You basically just add 5, so you basically just push everything by, if you add a units, you basically just push a units to the right hand side, all right? So this is the shifted exponential, okay? Right, so we're gonna use the shifted exponential as our gx here. Okay, so let me see. Then so clear some space. Right, okay. So our Monte Carlo estimator, using the important sampling would be the following. HXFX will be this one, right? So I just put the indicator function at the back here, okay? Over gx, right? So gx is lambda e of minus lambda x, so xi subtract a times indicator function, okay? Over n, right? Okay, so this whole thing here is our the terms. Now, so this one, you notice that these two functions, right? When these two functions are equal to 1, then you can simplify that, right? So this will only make sense when both of these are 1, right? Okay, which basically means that your values of x, right? Okay, you notice this here. Your x values are drawn from the shifted exponential. Okay, your x values are drawn from the shifted exponentials, which means that your x1, x2, and all that, they are at least, they are more than 5. Sorry, they are more than 8. All right. Okay, because they start drawing from A. Okay, so we can simplify that by removing the indicator functions here. So basically the single term here that you want, right? So when you calculate the variance, is basically just 1 over n, the variance of this thing here, right? X e of minus x over lambda e minus lambda x minus a. Okay, right? So I just removed the subscript here, all right, for simplicity. All right, so basically you have to so this is your variance. Okay, so we want to, so just now we found that the variance of this is bounded by theta m minus theta, right? Where my m is actually the max of fx hx over gx, which is this thing. Okay. Right. So basically now you notice several things here. The first thing is this parameter here, right? Lambda, right? So we're going to choose values to draw from, right? And we are trying to draw from a shifted exponential with these parameters. This a is actually given in the question, right? But this lambda, right? We got to determine what is this lambda. Okay, because there are many exponential possible candidates from the exponential family. Okay, so you have to determine this lambda, right? Okay, it could be 1, it could be 2, it could be something else. Okay, so basically this means here we got to minimize the m, right, with respect to lambda. Okay, we got to minimize m with respect to lambda, so that this thing here is as small as possible. Okay, right? Your m is the max of this, right? But we have to choose the lambda so that this max is as small as possible, right? We don't want it to get very large. Okay, so that's the idea, right? So now basically you have a double. So what you, sorry, it's not double. It's called a minimax problem. So on one hand, you want to find out the x that maximizes this term here. But at the same time, you also want to minimize the max, right? So it's a minimax situation. So the minimax situation corresponds to a what we call finding a saddle point, right? So the solution is a saddle point. the solution to a minimax problem is a saddle point in so this function here is basically a function of x and lambda, right? Okay, so there are two parameters. So basically this is like some kind of you have some kind of a mountain and valley kind of thing in 3 dimensions, right? Where this is your function and these are your 2 variables, okay? So I'll show you how a saddle point looks like, right? So um,
Yes.
Okay.
Right. Okay. So so this is an R demo. Okay, to show you how the how to use importance sampling to do the comparison. Okay. So as usual, first we have let's say 10,000. Increase the font. Okay, so maybe a larger font here, right? Okay, so okay, then we simulate from the shifted exponential, right? Okay, so all of you know that we can actually simulate exponential from the normal, right? Sorry, the uniform 0, 1, right? So what's the transformation? So we're going to simulate uniform 0, 1, right? And then we're going to do a transformation to simulate our x values, okay? How do we get it from the uniform? So, okay, let's look at the exponential, right? So how do we generate exponential random variables from uniform? Anyone? So if you have uniform random variables, how do you transform them to get exponential random variables? Anybody wants to share here? Anybody? I'll ask a couple of students. How about Hasnim? Huh? Is Hasnim here?
Yes.
Yeah. So how do you get an exponential random variable from the uniform? You do a transformation, right? What transformation?
Inverse.
Sorry? So tutorial 1, what transformation do you use?
Inverse transformation.
Yeah, sure. So what is the form? If you have done your assignment 1, right? I don't know. You should be very familiar, right? Anyone?
Negative log x over lambda.
Okay, sure. So negative log of u will give you exponential 1, right? So for any general, you have to value, you have to divide by lambda, right? Okay, that's the way to generate your, you can check back the theory again, yeah? Okay, so now, just now in the case, our lambda was found to be 0.69, okay? So we divide by 0.69. This would generate an exponential random variable with lambda equals to 0.69. But what we want is a shifted exponential, right? Shifted by a amount, okay? So we just add a, right? In this case, our a is 5, right? Okay, according to the example just now. Okay, we use a equals to 5. So this is how we generate our shifted exponential from g of x. Okay. Right. So once you have this, the rest is not difficult, right? So what's the function that you have? Your hx fx is x power of 3 minus 1 times exponential minus x, right? And then therefore your hx fx over gx, and what's your gx? So my gx is 0. Okay, maybe it's better to write lambda equals to 0.69 so that you don't have to write 0.69 so many times, right? Lambda, so that will be lambda times exp minus lambda x minus a, right, which is 5. Okay, so that's my gx, right? So this is my hx fx over gx. Okay, so basically this is my impedance sampling and Monte Carlo estimator. Okay, so then I sum this thing and I divide by n, right? Okay, so I can use this to check. Oh, sorry, it's not uniform. Unit. R unit. Okay, let's run that again. Lambda. Okay. Okay, forgot to multiply here, so I might run this again. Okay, so I get a value of 0.249. Okay. Now, if you use the naive MC estimator, right, which is just now the one that you simply sample from the exponential, right? So maybe we call that double x exponential. So basically your double x, so you generate from the naive one would be just exponential 1, right? Okay, so log of u, right? And then basically we take xx power of 3 minus 1. Okay, so then multiply and then multiply by the indicator function, right? Now in this case, that would be your xx your xx, right, has to be larger than 5. Okay. Right, so this part here would generate 0 or 1s. Only for the 1s you will multiply it with this xx. Okay, so this will be your naive MC estimator that we looked at the beginning. So you can sum this and then divide by n. Okay, then let's check the result. Okay, it's almost it's quite close to the one that you got from impedance sampling, right? Which is about 0.24 something. Okay. Now, of course, we're not interested too much in the expectation, but rather in the variances. Okay. Look at the variance for this part, and then we compare the variance for hx, fx, gx. Okay. let's look at the difference. All right. Okay, look at the first one. Your variance is 9.8 something, right? This estimator has such a large variance, whereas your important sampling variance, right? It's very small. It's almost, I don't know, extremely small, okay? So this gives you some very interesting result here, which is that your important sampling, right, is very powerful for variance reduction, right? From a naive variance of 9, close to 10, it manages to reduce it like how many times? If you divide this, you can roughly check, right? It has reduced it by, if you take the ratio of these two things, it's reduced it by almost 35,000 times smaller. That's huge, right? Okay. So in terms of the percentage of the original, it's almost negligible. Okay. So this shows you how powerful your important sampling method can be. Okay. And as you can see the codes here, if you understand this properly, right? Generally, the theory that you did just now was just to get this parameters set. Okay. That means you set these parameters, right? This lambda was found by some theoretical work. But the rest of these things you have already learned, okay? These things, you look at the previous codes, they basically are about the same, okay? You just need to specify the functions, okay? And then the Monte Carlo method is still the same, right? You just basically average them out, right? And over here, we just need to check the variances, okay?